to today's video. Today we'll be looking at the counting bits algorithm. We are currently going through this Shem Prashad algorithm series here. Today we are in the 8th, which is the counting bits algorithm. If you like this kind of videos or you want to go through this series with us, I encourage you to follow up. You could subscribe, share, and watch the video. I also hope that if you have any question, you drop that in the comment section so that can engage ourselves together and try and come up with even better solutions. So go back to our question. The counting bits algorithm. It says that given an integer n, we are to return an array ans of length n plus 1, such that for each I, where I is from 0 up to n, we for ans at index I is the number of ones in the binary representation. So if we look at it, when we have our input as n equals to 2, our output is 0, 1, 1, and the explanation is because in binary 0 is 0, 1 is 1, and 2 is 1, 0 in binary. So in this first, we only have, there is no number of zeros, no number of ones, so the number of ones here is 0. For 1, the number of ones here is 1, and for 2, the number of 1 is 1. If you look at the next example we have for 5, so 5 we have 0 is 0, 1 is 1, 2, 3 is 1, 1, 4 is 1, 0, 0, 5 is 1, 0, 1. And if we look at this, the number of ones in 0 is 0, the number of ones in 1 is 1, the number of ones in 1, 0 is 1, the number of ones in 1, 1 is 2. We have just 1, 1 here, and we have 2, 1, that is 1 here and 1 here. And that's how we form this array that is the output. So let's see how we could solve this. So we have but let's look at it. I think so we are given, okay, we are told that n is 10 raised to the power 5. Is there anything? So it says it is very easy to come up with a solution with a runtime of n log n. Can you do it in linear time and possibly a single pass, so O of n? And then can you do it without using, okay, so I don't think we have something like this. So in a single pass, and that is O of n. Let's see. We have n equals to 2, and when n is 2, we have 1. So we're starting from 0, 1, and 2. So it's going to be 0, 1 is 0, 1, and 2 is 1, 0. So we have 0, 1, and 1. So our answer for this is 0, 1, 1. When n, let's put this like this way. When n is 3, we have 0, 1, 2. So that is 0, 1, 1, 0. 3 is 1, 1. And so this is going to be 0, 1, 1, 2. So let's just go for something like 16, 15 rather. So let's go 15. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay. So for 0, this is 0, 1, 1, 0, 1, 1, 100, 101, 110, 111, 1000 here. So we have 1001, we have 1010, we have 1011, we have 1100, yes, we have 1101, 11, this will be 10, and then 15 is 1111. So let's see. Here we have just 0. We have 1, 1. 1 appears 1 time here, it appears 2 times here, it appears 1 time, it appears 2, it appears 2, it appears 3, it appears 1, 2, 2, 3, 2, 3, 3, and 4. So if I put it together, so our answer will be something like 0, 1, 1, 2, 1, 2, 2, 3, 1, 2, 2, 3, 2, 3, 3, 4. So this is what we have here. So if we look at what we have here, so let me just shift this a little here so that, so we have this. And if we look at this, so you remember that in binary is 2 indexes, so 2 raised to the power of n is what we have in binary. So 2 raised to the power of 0, 1, 2 raised to the power of 4, for example, will be 16. 2 raised to the power of 4, 2 raised to the power of, let's say, 2 will be 4, for example. Put this somewhere where we could, I just push this so that we have some space here, and I have this. So we have, because I want this to come out. Oh, sorry. Let's go again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let's have in here. I think 0, 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yes. So we have 0, 1, 1. I'm copying what we have here in our series. 2, 1, 2, 2, 3, 1, 2, 2, 3, 2, 3, 3, 4. And we'll see a pattern here. So don't forget I said that we have 2 is, for binary, it's in the powers of 2, right? So at the beginning we have 0. Okay, that's fine. But 2 raised to the power of 0 is what? 1. So it means that if we go one more step from here, so after 0, if we go one more step, I'm starting again. So if I add 0 to, if I add 1 to what we have here, that's how we have 1. So that was 2 raised to the power of 0, right? If I go for 2 raised to the power of 1, 2 raised to the power of 1 is 2. So it means the next 2 items are covered there. So 2 raised to the power of 1. So for example, for this next 2 items, I restart again. So I start with the first one, is going to be 0. 0 plus 1, I have 1. So if you are permit me, so I have 0 and 1 already. So we are here now where we have 2 raised to the power of 1, which is the next 2 items. So for the next 2 items, I know that I could start again. So that's 0 plus 1 gives me 1. And then the next item is 1 plus 1 gives me 2. I've exhausted that. So 2 raised to the power of 2 will be what? Will give me 4. So for the next 4 items, I know I'm starting again. So I start again. This is 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 1 is 2. And 2 plus 1 is 3. And I have it up to this point again. So at this point, so whenever I get to the end of a power, for example, 2 raised to the power of 2, 2 raised to the power of 3, I see that I'm starting from the beginning again. So when I go to 2 raised to the power of 3, I have 8. So that is the next 8 items. I start 0 plus 1 is 1. 0 plus 2, sorry, 1 plus 2 is 2. 1 plus 1, sorry, is 2. 1 plus 1 again is 2. 2 plus 1 is 3. 1 plus 1 is 2. 2 plus 1 and 2 plus 1 is 3 and 3 again. And then 3 plus 1 is 4. So basically you see that the pattern is that when we reach a point where we are the complete for the next 2 raised to the power of a particular index, 2 raised to the power of a particular number, and progressive, so from 2 raised to the power to 2 raised to the power 1 to 2 raised to the power 2, 3, 4, and going upward, we are repeating actually what was before and then adding 1 to them. Basically, that's just basically what we're doing. And that's actually how we solve this algorithm. So if we go to our LeetCode page, we have here that we have to return an array, right? So let's say response, and then we have, it's going to be an integer, and you remember we're told it's going to be of size n plus 1. If we check here, we're told that it's going to be length to be n plus 1. So So let me just return this response at the beginning just so that we don't forget that. So basically, what we want to do is that we know that the first index is going to be 0 already. So we could just start from 1 all the way to n. So we could have it like this. And we know we were keeping track of the power of 2. So for example, let me just have power. So at the beginning, I know my power is 1. That is 2 raised to the power of 0 is 1. So, and what I just want to do is, for example, if my I is equals to the power. So for example, index 1, that is 2 raised to the power of 0 is 1. 1 is 1. So at each time, when I'm at a particular, I want to move my power. So I know that my power is going to be just multiplied by 2. That is, I'm raising it to another power. 2 raised to the power of 2 times 1 will be 2. 2 times 2 will be 4. 4 times 2 will be 8. So that is just increasing the power by 1 time and moving forward. So we have that. But what we want to do is, at any time we are moving the power, we want to restart again from the beginning. So we could just have refresh. So that at this point, we know that refresh will be equal to 0. So what we want to do is that for each time, we just want to go through our response. We are currently where we are currently, and we want to start from where our refresh is. So our refresh will be 0 at the beginning. So for example, and plus 1. I know we need to increment our refresh so that. So basically, here we're just saying that so for example, when we have, so if we go back to our board, if you look at where 2 raised to the power of 1, 2 raised to the power of 1 gives us 2, right? So if you look at it, this is 0, 1. At index 2, we know that for the next 2 items, we have to go ahead. So we go 0, index 1. So this is index 1, index 2, 3, 4, 5, 6, 7, 8. Let me just stop there. So when we get to index 4 again, you see here at index 4, we know that we have to start afresh again. At index 8, we know we have to start afresh again. So you see, at each point where we are those powers, we know that we have to start afresh. So we have to refresh again. So basically, that is why here we see we're checking if the index I am at is equal to that power. So for example, at the beginning to be 1, index 1, then it goes to index 2. We know we have to refresh again. At index 4, we know we have to refresh again. Then at index 8, index 16, it's 16, index 32, going forward like that. We have to refresh. So at those points, we refresh again, and then our refresh goes back to 0. So if we start from beginning again to start populating the new indexes that needs to be filled. And let's see what we get here. So it passes. But this is going to work fine, I think. Let's submit it and just be sure that it works fine. Let's see. Does it work fine? Yes, it does. Yes, it does. But there is just something I just want to bring to our notice. I want us to look at the board again. So I will just pull this back so that we can just see this. If you look at, so we are keeping track of the power. So for example, we're multiplying, if you look at our algorithm, we're multiplying 2 by powers of 2 to keep track of when we are those particular power points. So 2, 4, 8, 16, we are keeping track of that using this power variable. But there could be another way. So if you look at what we have here, if you look at, for example, the first power way was 1, right? So if you look at 1, if you sum up what is at 1 with that is in binary 1 plus binary 0 will give us 1, which is index 1. If you go to that of 2, if you sum up 2 and 1, that is, if you see 1, 0 plus 1, 1 plus 1 gives us, so that's 1, 0 plus this will give me 1, 1. That is going to be index 3. So you see, so if we look at this, when we are at index 1, if we do an AND operator, so for example, binary of 0 and 1, binary of 0 is 0, binary of 1 is 1. If we do an AND operation here, 0 and 1 will give me 0, right? that will be index 0. You see, it gives me 0. It refreshes back to 0. If I go to 2, index 2, 2 and 1. So 2 in binary is 0, 1, 0, 1 is 1, that is 0, 1. If we are to do an AND operation between the, that is 0, 1, 0 and 0, 1. 0, 1 is 0, 1, 0 is 0. Remember, for AND operator, both must be true for it to be true. That means both we must have 1, 1 for it to get a 1. Otherwise, it's going to give us 0. So you see, this goes to 0 again. If you go to index 4, if we go to compare 4 and 3, 4 is 100 and 3 is 0, 1, 1. If we have a hand between this is 0, 1, 1. You see, this is 0, 0, 0. So you see, at every point when we have a power, for example, 1, 2, 4, you see, it refreshes back to 0. Or let's do for 8, 8 and 7. So 8 is 1000 and 7 is 111. That's 0, 1, 1, 1. So that is 1, 0, 0, 0 and 0, 1, 1, 1. And this is 0, 0 and 1 is 0, 0 and 1 is 0, and 1 and 0 is 0. And then we have it. So you see, at each of these indexes where we have the power, if we do an AND operation between that index and the previous index, it always gets back to 0. And then to start building up to 1, 2, 3 again. And each time it will read, by the time it gets to 16, when I do 16 and 15, it will refresh back to 1. If you do 16 and 17, it will be 1, and going forward like that. So we could use that to be like our refreshing, what we used to refresh. So basically, if we have this now here, so what that will mean for us will be that we don't need this and we don't need to keep track of this basically, and we could just have our refresh. So we don't need to have refresh like this. So we could just have something like a variable here, refresh, and for this refresh it will just be our I and the previous index. So the index we are and the previous index. This is a bitwise operation, not the logical operator. When we have this is when we have a logical operator, but this is a bitwise operator. So this we do, for example, 4 and bitwisely 3, which will give us 0. So this will refresh back to 0. And then if we keep incrementing till we get to the point again, it will refresh again. And this also will be, so let's just run this and see. See, it passes, and if we'll submit, you still get it to pass. You see, it also still passes. So we could use this approach. The reason why I'm bringing this up is because I want us to see that there could be future algorithms where we will need to apply this, and that's why I'm bringing this up now. So you see that at every point where we have a power of 2, when we have a bitwise AND operator between that index where we have a power, for example 8, and the previous index or number, which is 7, a bitwise operation between 8 and 7 will always give me a 0. A bitwise operation between 8 and 9 will be 1. Between 9 and 10 will be 2. And in that order, it will keep increasing till it gets to 16 again, when it resets back to 0. And from 0, it will increase again up to 16 till we get to 32, where it resets back to 0. And at 32, it will go to 64 before it resets to 0, to 128 before it resets 0, and keeps going that way. I hope this was insightful and helpful. If you like this kind of videos and you want to build your algorithm skills, I encourage you to follow, share, subscribe, and like this video. If you have any questions, you can drop them in the comment section. I'll be very pleased and happy to respond to all our questions. Thank you, and see you in the next video.